Hello and welcome to this fourth feature engineering lecture in this course, Master in Artificial Intelligence. So, in this lecture, we will now talk about how to reduce the dimensionality of the feature space uh, while preserving as much relevant information as possible. And as you can recall, we are doing this after having generated a lot of features to brainstorm in the feature engineering step after the first understanding the data and the problem and exploring data. And the brainstorm features, that we selected some important features, and in this we are further reducing these dimensions to probably the most optimal number of dimensions that can explain as much information as possible with as less number of dimensions as possible. So how to do that is the question. Any thoughts? So you can use, there are techniques that you can use now. There are techniques like principal component analysis. Also, there is a technique called T-distributed stochastic neighbor embedding and singular value decomposition. These can be used for dimensionality reduction. How? Let's take a look at each of these. And these days, most of these are available in various algorithms and programs, and you can directly use them by using the right program. And that's what we will show you as we go forward. So the question is, how can you use principal component analysis? So first, let's understand that PCA is a linear technique, linear dimensionality reduction technique. Now, which what it does is it finds the principal components, what is called orthogonal axis, in the feature space that captures the maximum variance in the data. So it typically finds the principal components of the feature space. Now, how can you do that? You need to run the program in sklearn decomposition, import PCA, and then you assume X contains your features, initialize PCA with desired number of components. If you want two components, put n components equal to 2. If you want more, you can do more. And then fit PCA into data and transform it, and you get your two main components or three or four main components, right? Similarly, let's look at T-distributed stochastic neighbor embedding, TSNE. Now, it's a non-linear dimensionality reduction, whereas PCA was a linear dimensionality reduction technique. Now, this also helps you map high dimensional data to lower dimensional space, and it preserves the local similarities between the data points. And again, it is now programmed, it's available for you in any of the programs. And what are the commands you need to do in sklearn? Let's take a look at that. So again, you assume X contains your feature, you import TSNE first, then you initialize TSNE with desired number of components. Again, you can choose 2, 3, 4. Then you fit TSNE to data and transform it, and voila, you have your answers. Obviously, you need to check it. Life is not that simple as I'm making it out right now. Then the last one to look at is the singular value decomposition. Now, it's a matrix factorization technique that decomposes a matrix into three matrices, allowing for dimensionality reduction by selecting a subset of components. So you feed the data, your y and x's data in a matrix form, and then you get your three principal matrix components of the factors of the matrix that allows you to reduce dimensionality. Now, how can you do that again? You need to rely on your programs. So here again, you can use sklearn by importing truncated SVD, import assume X contains your features, initialize truncated SVD with desired number of components. In this example, it is 2, and you fit SVD to the data and transform it, and you have your answers here. So for selecting the number of components, you can use PC and SVD as based on the explained variance ratio and principal and cumulative explained variance. So basically you look at what percentage of your variance in the data is being explained by your factors or variables that you have selected. For TSNE, the number of components is already specified beforehand, and it is typically based on the desired dimensionality of the lower dimension space. So you say, I want a 2-dimension space, I want a 3-dimension space, I want a 5-dimension, and for then the TSNE drives accordingly. Now, what is this principal explains variance? Let's quickly capture. So what is the explained variance technique? So in PCA explained variance technique, you look at the components, you look at the various components, you run the program for different levels of components and see which at what, so each each component numbers give you a certain explanation level of the data, and individually for each component and cumulatively, and you can map this and you can select the number, right number, based on the percentage of explanation that you want. So after running those programs and getting the number of components and deciding on number of components that is give you the right dimensionality reduction, you need to visualize the reduced component dimensional data using scatter plots or other visualization techniques as illustrated you in the program given below. And there you basically assess the separation or clustering of data. You plot the transformed data points in a reduced dimensional space, color them according to the target variables or cluster levels, and that gives you further insights into the data. Then you need to model the program, because ultimate purpose of reduced dimensionality is to see whether you have an optimal model, right? So then you use the reduced dimensional space data for downstream tasks such as classifications, clustering, or visualization, and you train the machine learning models or apply clustering algorithms using the transformed data to perform tasks on the reduced dimensional space. So final proof of pudding is whether your model is working well as TDM. So summarizing, we apply techniques like PCA, T-sign, TSNE, and SVD for dimensionality reduction, and with that you can effectively reduce the dimensionality of your data while preserving important information or structure, facilitating visualization, and improving the efficiency of subsequent machine learning tasks. So remember, the dimensionality reduction is not for the sake of dimensionality reduction. It is to improve the efficiency of your machine learning model, machine efficiency and effectiveness. So what do we do next? We come back to evaluating the feature importance, and we will see how it is different from the feature importance that we did earlier. And and this is after we have done the dimensionality reduction for optimal model performance. So thank you so much for watching this fourth feature engineering lecture in this course Master in Artificial Intelligence. I hope you're continuing to learn new things, continuing to enjoy. And I do look forward to see you again in the next lecture. Please feel free to message me if you have any questions to answer. And take a look at, download the PDF file to take a look at those commands that we gave for running the various tests in this case.